Okay. Welcome to the class. Let me start with maybe recalling where roughly we are. Point out. Okay. Well, where we are and what are we sort of skipping for now, and where we're going with the material. So. Okay. So you know what a PRG is, pseudorandom generator, and you know that it implies indistinguishable encryption. So that was a one-time encryption. And what was the construction? Stream cipher. And you also know that actually PRG can be constructed with just a tiny PRG, one bit extending PRG, right? So these were the various small PRG to large PRG compilers that we've seen, and that basically this is how stream ciphers really operate. They run these little guys inside to generate a pseudorandom string, and this is just XORing with a message gives you an indistinguishable encryption. We also have seen that PRF, if you have a PRF, then you have a CPA secure encryption. So this is a multi-use encryption, right? Where you can use it many times with the same key. And an example of the construction was a randomized counter mode. Okay. What else do we see? That if you have a permutation, well, you can also have CPA encryption. Well, first of all, because you have permutation, so you have a PRF, so you can use it in the same way, so randomized counter mode. But you can also use it directly. This was a CBC mode. And by the way, the book has one more mode that is also commonly used. I mean, commonly, okay, it is used. And it's sort of funny because you say, okay, how can I create yet another way of chaining PRF outputs? But you can, it's also very natural, and it's called output feedback mode. Okay. So far so good. We have this multi-use encryption now. And was there any way to hook this up? So basically how to construct a PRF, and thankfully, yes. So we also know that this is the trivial reaction. The moment you have a PRF, in fact, deterministic counter mode of a PRF just gives you a PRG straight away. That was the first construction for how to do indistinguishable encryption. You just use PRF in a deterministic counter mode, and you derive essentially a pseudorandom string, which you XOR with a message. But this was the non-trivial direction, right? This is the tree-based construction that we saw last time, and this is a really beautiful, simple and yet powerful mechanism. This was the Feistel and Lubirakov claim about it. I mean, the analysis. Okay, where 3 rounds of PRF in the Feistel construction gives you a PRP. Okay, so maybe what is, where are we going with this? Because we seem like, we have a very, very powerful thing. We have a key, and now you know how to use it to encrypt any number of messages you want with very small overheads of a randomized of a random IV that you have to use per each message. And you know you cannot get away with it because any deterministic encryption has to fail this notion. Okay, so well, where do these things come from? That perhaps is one question. Okay, how do you construct a PRG? So, well, you construct them by all sort of mysterious, you know, hacking and statistical analysis of some mysterious circuitry. But you also have some guiding principles for how to do this. And one guiding principle that you can that we can all understand is the Goldreich Levin analysis, or Levin, I think, put in this way, analysis of something called hardcore bit of something even simpler than a 1-bit extension PRG. That's called a one-way function. And its variant, similarly to here, one-way permutation. So what Goldreich-Levin really show is this implication, that the minute you have a one-way permutation, you can construct a PRG, a minimal PRG, but that is okay because you can run it and you get a PRG of any with any arbitrary output size. And thereby basically you get everything else. So this is enough to hook all of this up. There is some distance between these, and you know, there is a lot of work on abridging between these two. It's not they're not fully equivalent as of now. This we will come back to. Okay. It does simplify intuitively. A PRG asks you, okay, I have some circuitry such that if I feed it with random seed, the output is indistinguishable from a random string. That is a complex notion. Is that you have to consider all statistical tests. What does it, you know, to test it? It's not so fast. How do you test a statistical test exactly? Well, no, I take it back. Well, you can, but you know, mathematicians don't think of, is there some functions whose, if I look at their outputs applied to randomly sampled inputs, do these outputs look like random to any efficient algorithm that tries to distinguish them from random? This is some question that like never comes up in mathematics, okay? Unless you study cryptography and then you see its relevance. What does come in mathematics is that you have some transformations, some functions that on some from some inputs to outputs that appear easy to compute one way, but hard but hard to invert. And that is something that is very, for example, if f takes two numbers, x1 and x2, and outputs the product, then f inverse factors the input into its factors. So everybody knows how to multiply. That is efficient, right? Given the description, if I have n bits for x1 and n bits for x2, multiplication, I know how to do it in polynomial time of n squared or less. But if you give me, for some sizable fraction of this domain, the inputs here are 2 primes. Therefore, sizable fraction of this codomain are products of 2 prime. And mathematicians do not know fast any algorithm that would factor product of 2 primes in general. They have some heuristic for some, but basically we don't know fast algorithms for that, polynomial time algorithms. And that is a much simpler problem to state, right? Because it has nothing to do with something being pseudo-random, differentiating it from a random string. It's a simple computational question. Can you compute this function on all elements in the codomain, or you fail on some fraction of the codomain? And very simple algebraic stuff. Actually, we don't know how to invert, because that's factoring. Another example is f of x is defined as g to the x mod p prime, and g is a random number in the p star, which is this set 1, p minus 1. So prime, okay, and actually it doesn't have to be random. And for some choices of both the prime and this number, this function, so the exponentiation function is a function from z p minus 1, so all exponents which are smaller than p minus 1, to this set, right? Because modulus, you always are going to get a number smaller than p. Okay, and it is a fast function, so we know how to efficiently exponentiate. Even if this has n bits, and this has n bits, the algorithm for doing this is polynomial in n. It's actually n cubed. F inverse is called discrete logarithm. And f prime is the factoring. And discrete logarithm, for some choices of primes and some choices of this, we call it base of exponentiation. We don't know polynomial algorithms to invert this. And these type of problems are what mathematicians focus on in number theory, not some constructions that build, stretch a seed and claim indistinguishability of the result from a random string. But thanks to this beautiful stuff, you can take any of these. And why is this called one-way function? Well, as the picture shows, you can efficiently compute it one way. The inverse exists, it's well defined, but we don't know efficient algorithms to perform them. Likewise, here, the discrete logarithm. So I give you the result, and you ask me, what is the x which makes g exponentiated to that x equal to the result? I don't have this algorithm, right? So the function is one way, as in you can compute it forward, but there is no efficient algorithms to compute it backwards. Okay, and so that's called a one-way function, and it's a much more fundamental hold on, let me try to stop. Much more fundamental concept, and you can build a PRG from it, and you can build all this other stuff from it. So, whereas which also, you know, even if you don't, these results, even if you don't want to base your PRG on some mathematical function like this, you can use the same result, instead instantiate this with some, you know, complex looking hardware, circuitry, right? That perhaps doesn't use these, you know, complicated algebraic operations, but you have some guarantee that, well, not guarantee, but some basis to believe that this computation is in one way, but hard back. That suffices to create a PRG and the whole rest. So we'll get there later when we start, when we look closer into these one-way functions, because actually these functions will be used also for public key cryptography. So that would be an occasion to revisit this. And today I want to do two things: look into the circuitry of DES to see how these this, you know, design principle is reflected in a circuitry of the of DES. And I want to define a stronger notion of encryption that is, it's called chosen ciphertext attack secure encryption. And of course, we will want to build it. But at first, we will show that just like we showed that in the synchronous encryption is not necessarily CPA secure, but the opposite is true. Every CCA encryption will be secure in this sense, but not vice versa. And we'll see that basically all constructions we have fail this security criterion. Okay. So of course, we'll come back to this as well. Okay. This is. Do you have some questions on this? You know, short review of where we are. Do you see now the slides or the piece of paper? Okay, great, thanks. Okay, good. So let's go into the first part, the DES. Okay, and by the way, everything I was saying before, like you know, on the syllables, I'm marking. It's the same terminology, and I'm marking like this is described in this section, this is described in that section. So hopefully, you can orient yourself as to you know, where this stuff is reflected in the textbook. Okay, let's look at DES. So little history. It was designed in the 70s. There was a Lucifer particular design at IBM, designed by Feistel, and not surprisingly, you know, the one element in it, which is Feistel permutations, is because it's from the name of this designer. It had big bit lengths and blocks, and the National Bureau of Standards scaled it down, and that was like endlessly controversial decision, and the belief is that they wanted to scale it down so that it's possible. It's good enough so that it cannot be broken by others, but perhaps it can be broken by them. And as we looked, it's broken by exhaustive search, and there were two ways. So you could replace it by doubling the size of the key or tripling, right? The triple DES or DES-X designs we looked at last time, or a new encryption standard altogether. The cipher called Riandel was called, I think, A encryption standard. So A is oh, I forgot what A stands for. Okay, sorry, I blanked what A stands for in the AES. Okay, so the basic circuitry of DES uses Feistel permutations. So it creates these scrambling functions, PRFs, D rounds, and then it uses an invertible scrambling. It creates an invertible scrambling function from these, and it does so by the Feistel permutation, which we covered last time, right? So the point is that if you run, you can compute the circuitry forward, compute F1 XOR, compute F2 on this register XOR, etc. But you can also invert it, right? So if somebody gives you the output, so a decryptor would be getting an output and knowing the same keys, which are the keys of F1, F2, ... to FD, you can invert it because you can compute this forward on this register XOR with that one, and you're getting these, and then you recurse going back, right? So we covered this last time, and we said that if FIs are PRFs, then the whole thing is a PRP. And for strong PRP, which in Dice that's what you use. So if you recall CBC construction, basically, oh, okay, you know what? No, I take it back. So I think CBC construction, the security proof only assumes that it is a PRP, not necessarily a strong PRP. Okay. Here is the actual DES design. This is a picture we've seen before. When we introduced block ciphers, I said they typically use the key, they expand it into keys for multiple rounds, and then they use these for so-called round functions. Well, now you know, and we said this key expansion is a PRG. So it takes the key, 56 bits in the DES case, it runs this circuitry that basically implements a PRG and creates 16 copies, 16 new keys, so to speak, right? And which all together look like independently chosen random strings if the key K is randomly chosen, right? If this is a random seed to the PRG right here, and if the circuitry is indeed a secure PRG. And then it uses these keys to instantiate these 16 keys to instantiate 16 round functions. And how does it do so? The I function is, they're all instances of the same circuitry, of the same PRF. But to the I function is this instance of the circuitry with I of these keys. And here there's basically a Feistel. Now there is two more things happening. The input block 64 bits is permuted by something called the input permutation, and on the output you have the same permutation inverted. So it's a fixed circuitry that does not depend on the key that implements this permutation. And basically, what this is a matrix 64 by 64, which tell which of these bits are going to be translated into which of the bits here. Okay, so it's a linear function. Basically, it's a matrix multiplication. Okay, and we can invert using the circuitry. The only thing is that you have to, invert the order of these keys. Now, why is 16 rounds? Okay, look, there are 64 bits here. So if you feed them into Feistel, remember Feistel, it divides the inputs into two parts. So if this is 64 bits, then this is just 32 bits. Each of these functions is just a function from 32 bits to 32 bits. Now, this might raise an alarm, because how can an object that is so small, so okay, this circuitry design asymptotically, what is even a PRF? It's an asymptotic notion. When instantiated with security parameter n, an algorithm which asks the number of queries, which is polynomial in n, he cannot tell outputs from random strings. So one thing about inputs which are so small, where n is just 32, is that, well, maybe you can ask on all, right? Because there's only 2 to the 32 possible inputs here. Does that really mean that it is necessarily broken? No. PRF actually makes sense on small domain and a small range. So PRF, remember the tree-based construction. It makes sense to cut it at height, let's say 4. Then it's a PRF whose domain is just 4-bit strings. And well, how big are the outputs? Well, they could be only 4-bit strings, right? You can take a PRG and you just output the first 4 bits of its output. So there's nothing wrong with this. The only thing that cannot be short is the size of the seed. And the seed, in this case, right? So in other words, the key of the PRF. So that by itself is not yet a reason that these little round functions, in the case of DES, cannot possibly be secure PRFs, because the bit sizes of inputs and outputs of these would-be PRFs is so small. It's only 32 bits. So I'm juggling between notions like a PRF, which are asymptotic, and concrete instantiations of these notions with bit sizes like 32. But hold on just a second. I have to sorry about that. But intuitively, the best you can. Okay. Anyway, hopefully you follow. So we cannot. So this is not by itself a counter argument, but yet these functions are if you instantiate them with a however long key here, they are not in themselves a full-fledged PRF. So you would have attacks against them that are much faster than search for the key. That's why DES has many more rounds than Lubirachov would recommend. And indeed, analysis of DES, crypto analysis of DES, proceeded in sort of similar ways to when I was talking about the Feistel, saying that, if you stare at the circuitry, you will see that 2 rounds are not enough. So there are some insecurities one can exploit. 3 rounds is probably enough. If these FIs are weaker functions, the attacks essentially, the challenge is to that people currently can, let's say, the first 10 rounds, they can show quite feasible attacks that basically are faster than by exhaustive brute force attack against the key. But they do not know how to extend it to 1 more round. And then the next batch of cryptographers comes up with an improved analysis, perhaps some new ideas in that analysis, and they can analyze more rounds. Once the number of rounds for which cryptanalysis exists is close to the number of rounds in the actual construction, the people who use it should run and should replace it with some other design, because a full break is basically around the corner. Okay, and I don't remember right now, sorry, how many rounds of DES are essentially broken. So this is sometimes called, in cryptanalysis, is referred to as round reduced, analysis of a round reduced version of DES. Let's pretend that it has only 13 rounds instead of 16 and see if we can attack it then. Now, what do these functions look like? So what I'm talking about is the round functions in the Feistel. They're all cases of the same function. They're just instantiated with a different key. Okay. So as I said, the input block is 32 bits, right? 64 divided by 2. And the round key is 48-bit long. And already that is, is a too small thing. So a brute force search against that is possible, but that is a brute force search against, a round key, right? And attacker could perhaps, let's say you are a PRF attacker, so you can specify the registers here, but you don't control. So okay, so that of course controls the input to the first PRF, right? Because it's just the higher register after the permutation. This will tell you what the register is that FK1 acts on. But you don't see the intermediary results, right? You know what the R0 is, but you don't see this wire, right? This is the internal wire to the circuit. So you don't know what was applied to F2, and you know even less about the subsequent ones, right? All you know is the output, final output. So after 16 rounds of this stuff, right? So just because this key is kind of short, it doesn't mean that there is an attack, because you don't see the intermediary output, intermediary wires. Okay. How is this key used? So first, this input block is expanded, and this is again a matrix multiplication, right? So it just takes some bits here, and some of them it just shifts, and some of them it copies. It shifts and copies. Okay. Then so you got this translated into 48 bits, and all you do with the key is you XOR. And that's the only way the key comes in. It is basically like a one-time pad, an input pad, right? And that is also because basically the round function is the fixed computation, and what happens with the input is that, let's call it C. This whole circuitry, let's call it C. So the round function looks like, given an argument X, you expand it, but let's forget about it. You take an X and you XOR it with the key K, and then you output C or apply to the XOR between X and K. Well, can this be a PRF? Well, that seems like a very, very simple operation, right? You use the key in a very simplistic way. Compare it to the tree-based construction of a PRF, right? The key was used in a PRG circuitry, and the input was used to just decide which output of the PRG subsequent output should be taken. Here, there is something much simpler, and yet still, even that is not an immediate place to attack this as a PRF, because the attacker doesn't know this key, right? The attacker specifies X's, and what he gets back is C applied to X XOR the key. He doesn't know the key. So this circuitry C gives him outputs on different inputs. The inputs are very strongly related. If I give you an X and then an X XOR delta, the C is run on one argument in one instance, and then on the same argument XOR delta in the other instance. So I know exactly the differentials between all the inputs into the C. And the C is public. Everybody knows the circuitry. But so what? If the inputs are long enough, I cannot locally recompute all the C's, all the C on every input. Actually, right here, you can see 2 to the 48 is not much. You could indeed have these huge tables of, right? So therefore, basically, there is a feasible attack on this circuitry as a PRF. But then, again, that doesn't suffice because you don't see the intermediary outputs in the file. But this can give you some inkling like why you need more rounds of this stuff, because it doesn't seem strong enough as a PRF. The circuitry doesn't sound good enough as a PRF. So you cannot just rely on a Luby-Rakov analysis, or otherwise 3 rounds would suffice. So what is this fixed circuitry that then runs? You divide these 48 bits into 6-bit blocks, apply small permutations that are called S boxes. Actually, sorry, they're not permutations. They are functions that take 6 bits and output 4 bits. And these are fixed functions that do not change from round to round, right? The only thing that changes is the key here. Think about a function from 6 bits to 4 bits. How many bits does it take to describe this function? Well, how many inputs can it have? 2 to the 6. There's only 64 possibilities of value on this wire. And there's 4 bits to describe every output. So these functions are just tables. They have 64 entries, as many entries as there's possibilities for this wire values. And each entry is just 4 bits. Yes. So 64 times 4 is 256. You can describe an S box using 256 bits, 8 bytes. They're tiny, right? S boxes are, you can describe them as 8. No. 6? No. What am I saying? No, not 8. 256 is 8 times 8 times 32. Yes, sorry, 32 bytes. Sorry. Yeah, you can describe an S box using 32 bytes. So it's not much. And indeed, that's how the pictures. So basically, you can think of this as a lookup table that fixes the value for every input. You just look up table, and this is the 4 bits that you output, depending on these. You gather them, you just concatenate them. You have 32 bits, and you have some output permutation. So they are not, this thing just concatenates them, but they basically are shifted around, right? So this is a fixed permutation, and that's it. Look, yeah. So here is the example of an S box. Like this is the 5th one. For I think the reason that how the hardware is built, I don't really remember that. They are portrayed as a table where the rows correspond to the first and the last bit. So you have 6 bits of input. This is the first and last, and this is the 4 middle ones. Okay, and you perform a lookup. So this will be an output on 0, 1, 1, 0, 1, 1. Okay. So this is just copying the bits. This is an XOR. This is a permutation. The whole complexity is in these S boxes, but they're very small. So why? Well, what would be the design principle behind an S box? So I will tell you what shouldn't be. I mean, when would an S box? What kind of thing an S box has to avoid, or otherwise there is an attack? It must avoid being a linear function. Suppose it is a linear function. Note that both E and P, so this and this, are linear functions. If S was a linear, if HSI was a linear function, what does it mean linear function? It means it's a matrix multiplication. So the input 6 bits is multiplied by a matrix, and that's how you get these. You can, if HSI is a linear function, then so can this whole computation be, right? Because focus, I hope so. But I don't know how to switch spotlight for everyone. Remove all pinned videos. Okay. Do you now have the large page? Does it show this page large on your screen right now?
No, it seems the slider was...
Oh, you can switch yourself?
No, the slides are large.
Oh, okay. Somebody says that you can actually switch. Nada says that you can switch.
Yes, we can switch.
Oh, okay. Good. Because I don't know how to do this. So if the linear function that operates is like this, here is your input, which is divided into these 1, 2, 3, 4, 5, 6, 7, 8. So these are the 8 blocks. This is your input X, which has 48 bits, 6 bits each. And what is the linear function that operates on them? Well, there is the S1 function that operates on this guy, and that's the output. So this is basically S of X1. Right? I divided my X into 8 blocks of 6 bits each. And then I have S2 here, which is going to act only on X2. So this will be the next thing that will be output is S of X2. Sorry, S1, S2, S8 of X8. Here is my S8, right? And everything else is a 0. So if SIs are linear functions, so you take a 6 bits and there is some 6 by 4 matrix that is SI, and that outputs the 4 bits of an output, then the whole this whole circuitry can be represented as a matrix. And so this whole circuitry is what is well, I take my X and I multiply it by an E, because this is the E is a linear function, and then I have to XOR K, but you know, I can do it like this. I take XK and I multiply by E and an identity. So now at this point, the output looks like E of X and K, right? And then I have to XOR them. Well, this is a simple matrix. What does this matrix look like? Well, the first bit is like this. The second bit is like this. So this matrix is basically stands for an XOR. So at this point, when I do this, then I have E X XOR K as an output. So in other words, this matrix multiplied by this identity it represents that guy. So now I pile this transformation S8, and I have the result, and then I take this permutation at the end, and this whole thing is a linear function that represents the round function of in DES. Let's go back to this slides. I guess if you can switch back, then please do. So if the SI looks like a linear function, so there is some matrix AI, and all I do is apply a linear transform like so, then the whole DES can be linearized, so made into a linear equation. Okay, and I was arguing that basically each round function, what I have on the slides here is on this white sheet, is a linear representation of this whole of the round function. And because this is linear, so a matrix that converts this registers into these is also linear, right? It's using the same trick to represent this function and an XOR as one backlinear function. And if I just pile the matrix that corresponds to this and multiply it by a matrix that corresponds to this, and somehow, in a very simple way, I take account of the switch, and I pile them up this way, what I get as a result is a linear function applied to this and to the 16 keys. And that's what I have here. It is some matrix that will take the input block and 16 round functions of DES and apply some linear combination on all these blocks, right? So this is 64 bits of input, and each of these guys have 48 bits. And output a 64-bit output. And because it's linear, it's mod 2, right? Because all I do is XOR. That's really the only operation I use. It's all XORs and shifts. And if this linearization existed, then DES would be insecure, because it doesn't matter what these 16 keys are. They can indeed be random keys or outputs of a PRG on a random seed, as is the case. It doesn't matter. Let's denote this 16 key expansion as key, K, and note that here is a relationship that you can compute that shows that this DES, which is not the real one, but the one that is linear, that would be the case if S boxes were linear functions, satisfies a property that breaks the PRF property of DES. So in other words, it basically shows that DES would not be a PRF. It would not be a secure block cipher, right? Okay. It could not be used in any of the designs we have, not in CTR mode, not in CBC mode, because all of them, their security analysis requires the block cipher to be either a PRF or PRP. So what's the attack? Let's look at the XOR between these three values. So DES K of M1 would be this matrix fixed matrix B applied to M1 with K. DES K of M2 is the fixed matrix B multiplied by M2 and this 16 long vector, right? And because of the linearity, this is equal to B times the XOR between these three values. But that is equal to, you see, K XOR K XOR K is just K. So this is true. And so for any 3 points on which you ask this k, regardless of k, you could combine them to create a value of this k on an argument that is an XOR between these 3. So this is an attack against the PRF, right? Because of course, a true random function would not have this property. Okay. So, so we know one thing, that right. So what's the attacker? He specifies M1, M2, M3, and M4, where M4 is the XOR between M1, M2, M3. And if the outputs of this challenger satisfies this constraint, then he knows that he's talking to an instance of DES. And if they don't, then he thinks that this is a random function. So it's a very efficient attack. So what do we know? That the S boxes cannot be linear functions. Indeed, even if they were quote unquote close to linear, what does this mean? Well, somebody writes this S box, and you are asked, does this represent a linear function on the 6 bits? So does there exist a 4×6 matrix such that all these outputs can be computed by multiplying the input bits by that matrix? Well, you can check this and you can search for such a matrix, but let's say there is none. So the S box cannot be represented as a linear function. What if for a substantial fraction of input bits of the inputs, so there's 2 to the 6, right, 64 inputs. What if there existed a linearization of an S box that worked correctly for 60 bits, for 60 possible inputs, and on 4 it just fails. So it doesn't model the S box. Well, you can see that the search space, I give you the S box, and you tell me what is the maximum number of inputs for which you can represent an S box correctly as a linear function. It's not so easy to tell, even to search for such linearizations. But if the S boxes were too close to linear functions, so on too big of a fraction, there existed a linearization of the S box, then you would still break it. And intuitively, you would break it because if the S boxes are on sufficient fraction linearized, then the whole thing is linearized on sufficient number of on a sufficient fraction of inputs. It's not as simple as that. So therefore, just by bombarding this with random, you are going to eventually sample from such subspace on which it is linear. But it's not as simple as that, but that's a basic intuition for why that could be the case. So apart from the fact that they should stay away from linear functions, there are also some other properties. There are sort of balanced, as in each of the S boxes is a 4-to-1 map. So, right, the input space is 6 bits, output 4 bits. So, on average, you would have 4 collisions for every range element, right? But this is actually exactly 4. There is a funny thing is that, you know, how would you design an S-box? Perhaps the most secure thing would be outputted at random. You know, randomly populates this table, right? And perhaps you should have good properties, good guarantees. Then it will, first of all, there is no some hidden trapdoor. And secondly, that any simple rendering of this, that basically it cannot be simplified because you populated this well by random. So how come it has any useful property? And that was actually violated by this result, because a random S-box is too close to linear with high probability. So if a monkey generated an S-box, that would be actually insecure. Well, maybe that's not surprising, but anyway, you population of populating S-boxes with random inputs would make it attackable. This is sort of an odd case, because sometimes you know, what is the, when people, you know, different security agencies or cryptographers or what have you meet and say, okay, it's a good design, but how do we make sure that you don't implant some trapdoor in it so that you can analyze it, but we cannot, because you generated these inputs with some hidden structure. Well, one way to guarantee it would be to let's coin toss and let's populate this input with random stuff. Then we all have a guarantee, if we all participate in this coin toss, that this has not been tampered with, right? And yet, these type of results shows you that such procedures are not guarantees of security. In fact, such choice would essentially be breakable. So this analysis came quite a long time after, about a decade after DES was standardized. And the beautiful thing that came out of this was, well, not only this, which is already beautiful enough, but that the S-boxes that were standardized in the mid-70s with the input from the Bureau of Standards and by extension, the National Security Agency, these S-boxes were optimized to be as far from linear as possible. Conclusion, they knew of this attack. Indeed, I mean, the fact that this, if this is linear, then this will be broken, is pretty easy to observe. What is harder is to derive all possible, you know, is to generalize this to boxes that are close but to linear, but not exactly. These S-boxes were seemingly designed, I mean, obviously designed with that principle in mind. And it's a case, this often cited, of cryptanalysis in the academic community taking a decade to catch up with something that NSA knew. This is not a general rule. I mean, you know, communicating with NSA is like one directional, right? Like we just don't know what's happening inside. So we don't know what they know and what they don't know. What we can tell is like from the designs, they approve or don't approve or whatnot, right? So it's not necessarily the case that they predict everything that they are ahead of academic cryptography in all cases, but they were in this case. Let me see how I'm doing on time. You know, I will briefly talk about AES. Unlike DES, it has a much larger block size, which we have seen why that would be important, right? Because of all the blocks, modes of operation of a block cipher are very sensitive to block size, because for the basic reason that collisions in blocks, collisions in randomized vectors, basically imply attacks. But not only that, it has a built-in sort of tolerance for that. Even if today we think 128 bits suffices against exhaustive search, there is already the circuitry and the software supports higher security modes. And that's because, first of all, in some constructions, you might need to rely on higher security modes because the upper layer of whatever you do with the block cipher perhaps requires the underlying block cipher to be more secure than you know, some other applications. In general, it's right. So we rather than, of course, we know that we can extend key sizes by a triple cipher or the cipher X, right? Or there's other compilers, but also the basic circuitry has this support for the increasing security parameter natively built in. Another thing about AES is that it's not a Feistel. So it is not a Feistel with a different PRF. It's a different design. It's still divided by rounds, but the round functions are so-called substitution permutation networks. So the way you use the round key is sort of similar as in DES. You take your input and you just use the key to XOR the input with. And so that's what you did with round functions of DES, essentially. But this S1 to S8 are this is the substitution layer. So it takes the input here, 128, is divided into 16-bit blocks, and these are the substitution. Basically, you can think of them as a 16-bit by 16-bit lookup table, okay, which is a permutation. And then this is a permutation layer. So you just shift this guy here, right? You just shift these blocks around, and then you XOR another round of the round key, and you recurse. Okay, and so this is the inner round function, and it has to be invertible. So the SIs are invertible. Do I have, okay, so the number of rounds here is smaller than in DES. So in DES I had 16, and okay, no, what, I forget how many rounds I do in AES, sorry. So here is the zooming on the blue block, so on the S1. so let's what these they do the following three things on three sequences of substitutions. First is the byte substitution, so it's 8 by 8 lookup table. Then so first you represent your input as 4 by 4 table of bytes. So 16 times 8, yes, 128. So it's a 4 by 4 table of bytes. First, you have a little 8 by 8 substitution lookup table. So every byte you'd look up in this lookup table what it substitutes with, and you substitute. Second, you shift rows. So one row is going to be shifted, the other stays, then the next is shifted by a more, basically this is not shift, it's a rotation really. So each row is rotated by a different amount. The third, you mix columns. So you permute columns, and then you do an XOR. Okay, and sorry, and now I have it. It's 10 rounds. I forgot. And how do you do this key expansion? So this is the same PR. I mean, it's not the same, but it is a PRG that takes a key and expands it into 10 rounds. Actually 11 here, okay, because I have this post processing at the end. Another I use this final key as a to post process. Okay, sorry. So my sound was bad. Tell me how far, you know, how much did you get the operations on the byte substitution, the shift rows, and the mixed column on this 4 by 4 table? Okay, I saw that there was a bad connection for a bit, but perhaps well, I should repeat that this key is expanded into the round keys using a circuitry that should be a PRG, exactly like in the case of DES. Okay, and here is the low zoom on the byte substitutions. So again, the inputs are 4 by 4 of bytes, and the byte substitution, okay, it's like a byte-sized S box. So it takes 8 bits and output 8 bits. It's just a lookup table. You know why the S boxes were only 32 bytes, I said, or yeah, and now I can have 256. Well, because a decade passed, and so it's okay to have larger, slightly larger, you know, both hardware and software, right? But even in hardware, these are small objects, and so you do the substitution, then you shift rows. You don't rotate the input first row, you rotate the second one by shift 1, the third row by shift 2, and the last row by shift 3. And you mix columns. So basically, you take the column vector and you multiply it by a fixed matrix. Okay, the matrix is an invertible matrix, so there is a way to go back. But yeah, but this is a linear. So it is a mixture of linear operations, like this one, and this one, right? Because you can represent these rotations in a linear as a linear function with non-linear operations like this one. And that's it is, you know, that's AES. And since it was standardized for now 2 decades plus, the attacks are on AES round reduced, but not full and not closed for now. I think that I should not start a new topic. I said that we'll look at the security of encryption against chosen ciphertext attack, but I think it makes no sense to try to start it in, you know, in 5 minutes. So this is something we should postpone till next week. And I will I expect I will send a new homework out and post on Piazza later today. Do you guys have any questions?
I wonder, when we choose the S box, you said we can't choose it randomly. So what's the criteria to choose the S
Yes.
box?
So, well, the criteria was there are some other forms of attack, and you know, I guess I don't know the full story. Like, I don't know if there were other criteria that were identified and that basically are not known in the academic community. But so first of all, I realized that I do not remember why this regularity 4-to-1 is a good thing. Yeah, I do not remember right now. But the criterion that I was going over is this one, that it has to be as far from a linear function as you can, which is not a trivial problem by itself, because it's not, you know, if I ask you, so it's a function from 64 inputs, yes, from 6 bits to 4 bits. And I ask you, give me a description of such function such that it maximizes the distance from the nearest linear function. Now, what do I mean by distance from a linear function? Here is the definition. Take all linear functions from 6 to 4. These linear functions are can be described as matrices of 6 by 4. So there's 24 bits that describe such matrix. As we said, there's 256 bits that describe an S box. So there's 2 to the, hold on, how big are S boxes again? Let's see. It's 16 by 4. So 32 times 4. Okay, I guess 128. Okay, maybe 128 bits. Okay, so anyway, there's 2 to the 128 possible S boxes, and then there is 2 to the 6 by 4 was 32. Yeah, 2 to the 32 possible linear functions. So you know that a fraction of an S boxes which are linear functions is tiny. It's 2 to the 32 over 2 to the 128. So a random S box is not a linear function itself. So if a monkey designs an S box, it's very unlikely that it designs that it's a linear function. But the distance from a random S box to the nearest linear function, where the distance is defined like this: what is the minimum number of inputs that I have to forget so that the rest is described as a linear function? The function on those, right? So I have 64 input possibilities, right? Possible inputs. If I strike out 5 of them and look at the remaining 27, is there a linear function that describes the function on this subdomain? It is not an easy problem. It's not an easy search, even for yes. And by the way, I do not know right now. I do not remember. What is the distance such that if I strike out enough of inputs, then with overwhelming probability, this function is linearized. So basically, I don't remember what is the maximum distance you can get from a linear function. But whatever it is, the S boxes that were created in the mid-70s were, maximum distance from a linear function. So that's one design principle. I'm not sure, how to do it. Like basically, what is exactly the search space? How do you search over the space of S boxes which are maximally distanced from linear functions?
Okay.
It's a complicated search space. Perhaps there are some heuristics. Perhaps they are not very maximally distanced, but sufficiently distanced. I'm not sure that any of these have. I don't even know whether there is sufficient algorithms to exactly tell how far you are from any linear function. Even though the space of this, I guess. Well, I guess you can. No, you know what? I guess you can, right? Because there's only 6 by 4, so again, that's 32. So how many linear functions there are? 2 to the 32. So that's 4 billion. So you write out 4 billion functions, and every S box you just evaluate. You take each of these 6 billion, 4 billion. You take a function, and you can tell the distance between an S box and that function, where the distance means on how many of the 64 possible inputs, does this linear function predict correctly the outputs of the S box, right? So basically, how many of these do I have to scratch out so that the remaining ones are explained by a given linear function? So for every linear function, I can get a score, and there's only, quote unquote, 4 billion of them. So I score it with each 4 billion, and then I know. Yeah, so I guess these are numbers, I don't want to code this, but you can, it's 4 billion lookups and 4 billion. Yeah, so you can probably code it quite fast. So you don't have to, you know, you don't have to have any sophisticated math to answer these questions. Somebody else is asking, I see a raised hand. Unmute yourself. Oh, I guess.
Sorry, that was just, yeah, an accident.
Oh, okay. Okay, everyone. So I forget whether it's book tells the story or not. I will check and send you a pointer if there's possibly other stuff about DES design in the book that I didn't include in the lecture. Okay, so watch out for the next homework and hang in there and stay well. I'll see you around.